this node is moving so little, you can approximate it as being a ground. So you can just take this capacitance as being connected to ground from Vn, and just use the value that you've calculated for that capacitor. Okay, and the last one is the CBE of Q3. Okay, in the CBE of Q3, you need to recognize that Q3 and Q4 make up an emitter follower. That means that whatever change on the base of Q3 happens, whatever change in voltage at the base of Q3 there is, that exact same change shows up at V out. So V out is moving the exact same amount in the exact same direction. Okay, so if you have two voltages, remember it's the difference in voltage across your capacitor that makes the difference. So if you move both sides of a capacitor, the delta V across that capacitor doesn't change. If both sides are moving together, the delta V across that capacitor doesn't change. You're subtracting this voltage from this voltage to get the voltage across the capacitor, and that doesn't change. So if you don't have any change in voltage across a capacitor, there's no need for extra charge, and that capacitor just seems invisible, and you can remove it from your calculations. Okay. So what we've seen if the far side of a capacitor is connected to an AC ground, you just take it as whatever value you calculated. We've seen in this last slide that if the far side of C moves the same amount in the same direction as the other side of your capacitor, then you can ignore it. It's not going to suck any charge off of anything because there's no voltage change across it. So you can ignore it, remove it from your calculations. If the far side moves a lot, for example, from the input of a common emitter to the output of a common emitter, the output's moving quite a bit as compared to the input and in the opposite direction, then you have to figure out what the change in voltage is across that and multiply your capacitor by that value. If you are at the output of a common emitter or a common source, and you move a little bit and you're looking at that capacitor that connects the output to the input, that input is not going to move very much. So you can consider the input side, so the far side, as basically ground. Okay, so to summarize, we've seen where the C comes from. We've seen the exceptions for capacitance, what we just talked about now, whether you can ignore it or you have to multiply it by some number, or whether you can use the actual value you calculated for that capacitance. Okay, we've seen where R comes from, just the small signal R from a node. We've seen that transistors act as low-pass filters, and we've seen that low-pass filters are poles on a Bode plot. In other words, the magnitude drops minus 20 dB per decade per pole. And we've seen the basics of a Bode plot, basically just for poles so far. Okay, so let's look at just a couple more events that you get on circuits. Started on this example in class, kind of got fell asleep while I was talking about it. But here's a system right here. Let's consider this A1 and A2 ideal amplifiers. Okay, we've kind of pulled out their R's and the important R's and C's from them, but assume that they are perfect. Okay, let's assume R1 right here is the output impedance of whatever's generating this voltage in. Okay, then assume the C1 is the input capacitance of A1. So R1's output impedance of your whatever's providing your voltage to your amplifier chain here, and C1 is the input capacitance to A1. Take R2 as the R out of A1, C2 as the input of capacitance to A2, R3 is the output impedance of A2, C3 is the input impedance to whatever circuits out here that your amplifier chain is driving. Okay, if you do that, let's see what happens. You have your V in right here, and it goes through a low-pass filter, and then it gets to the input of A1. So there's a little block here, this R1C1 filter here, that takes V in and gives you a V in 1. Let's assume VN1 is the input to A1. Okay, and then A1 takes its input, which is VN1, the VN1 generated by this low-pass filter, and gives you a VOut1. So that's the VOut1 is the output of A1. Goes through another low-pass filter, takes VOut1 as its input, and generates VN2, which is the input to A2. That's this term right here. And then you have VOut2 over VN2, which is the VN2 is the input to A2, VOut2 is the output of A2. And then you have this last low-pass filter that takes the output of A2, Vout2, and gives you your final Vout. Okay. You'll notice that this VN1 over Vout1, in other words, the input into A1 and the output into A1, that ratio right there is just the gain of A1. And then over here, Vout2 over Vn2, that's just the gain of A2. Right? So there's A1 and A2. These other guys are low-pass filters, and we've seen that low-pass filters give you an equation like this with a pole at omega equals 1 over R1 C1. And for each of those filters, we have a term for those two. Okay, if we want to find the magnitude for our Bode plot, we need to get rid of the complex, the imaginary part of these equations. So you multiply this by the complex conjugate, and for that, here's you have 1 plus j omega R1 C1. You multiply that by 1 minus j omega R1 C1, and you end up with 1 over 1 plus omega R1 C1 quantity squared. And then you end up with that for R2 C2 and R3 C3, and you take the square root of that. Okay, so if you put this all into a log equation, you have 20 log of, here's your two gains. They're constants. They weren't complex, so they weren't involved in getting rid of the imaginary values. A1 times A2, and then you have your magnitude calculations. It gives you this term. And here's the other part why Bode plots are popular. It's because if you have something times something times something and you take the log of it, that just means you take the log of each of those terms. You can analyze them all completely independently, and that's what happened down here. We have A1 times A2, and that's times everything else, so you can take that out, 20 log of A1, A2, and then this term turns into 10 log of 1 plus omega R1 C1 quantity squared, and then this is the second term, and this is the third term. Make sure that math makes sense to you. So now that you have your equation for your Bode plot magnitude, you can see a few things that are really important here. One is, let's say R2 C2 and R3 C3 are very small. Okay, and let's say R1 C1 is quite a bit bigger than R2 C2 and R3 C3. Okay, what happens is that as long as omega is small enough, such as these terms right here are way smaller than 1, they can be ignored. So if omega is way smaller than 1 over R1 C1, then this second part, this omega R1 C1 quantity squared, that can be approximated as 0. And then you just have log of 1. And log of 1 just equals 0, so this term disappears from the equation. If R2 C2 is really small, and omega has to get really big before this term has any meaning, and you just have another 10 log of 1, which is 0. And then same thing over here. If R3 C3 is very small, omega has to get very big before you have anything other than log of 1 here, which gives you 0. And so you start out when omega is much smaller than all of these guys, much smaller than 1 over the RC, you just start out with 20 log of A1, A2, which is a constant. So you start off your graph flat at 20 log of A1, A2. Okay.